Hi everybody, we are going to have our first lecture on design capacity and available pressure, focusing on metered municipal irrigation systems. And the screen looks a little bit different than it has in the past because I'm going to be showing you the lecture slides along with a worksheet that I'll be showing you how to use as we go through the lecture. So that's why things look a little bit different. We'll start with a couple of definitions. First, design capacity and available pressure. So design capacity, as you will have read in the module, is the maximum flow in gallons per minute available for use by the irrigation system. And it's really important because it's going to determine the number of sprinklers you can have on each valve in your system. So we are really starting to get to the point where we're making design considerations, and of course design capacity is going to be a critical part of that. Also, the available pressure lets you determine the estimated sprinkler operating pressure of the whole system. And you're going to use that when you're going through the process of choosing sprinkler heads. And it's also going to have an effect on sprinkler performance because sprinklers are specified to work at certain available pressures. So it's going to be critical as you begin the design process. Now, depending on the situation, there are three methods for determining design capacity and available pressure, and they really depend on the site situation. The first of these is a metered municipal system, and that's what we're going to go over in this lecture, but there are two others. One is when you might have an undeveloped site, and in that case you'd have to do an assumed flow calculation. We'll talk about that in the next lecture. And in the third lecture of this module, we're going to talk about sites where there are a lot of unknowns for you as the designer. There may be unknown components, valves, all sorts of things, and you might have to do an actual physical flow test in order to determine design pressure and design capacity and available pressure. So we'll get to those other two in the next lectures, but we're going to focus on metered municipal systems here. So I'm just showing you the worksheet here to remind me that I wanted to introduce you to it. This is the actual Excel worksheet over here on the right, and you're going to be using it to calculate design capacity and available pressure. And it actually has the calculations built in, so you won't be doing them by hand, which I suspect is a bit of a relief after the last couple of assignments. But before we get to that, let's go over a couple of definitions. First of all, here's this is a pretty simple example, but it illustrates everything you would see in a metered municipal system. First here is the water source. It's the city water main, and it brings water to the project. In this case, it's a home, and it's the water being supplied from the city. Now, in between that water main and the meter is what's known as a service line. And the service line connects the city water source to the meter, and of course the meter is where the volume of water being utilized by the structure is recorded. Now, beyond the meter there's another line, and that's the delivery line. It connects the meter to the point of connection, and the point of connection is the location where the entire water system of the structure is connected to the supply, so everything before this point. So it's really important to know what those are, particularly as we start working on the spreadsheet, because you're going to have to enter specific information about each of those. I think the simplest way for you to understand how to use the spreadsheet is to go through an example. So we're going to consider this pretend municipal metered system. I'll orient you a little bit to start with. So here you've got the water source, the city water main, and we know from the city that the pressure in that main is 80 psi. The service line, which is running from the main to the meter, is 1-inch type K copper, also information we've gotten from the city. It's 25 feet long. We also know that the meter is a 1-inch meter, and the delivery line running from the meter to the point of connection is 1 1/4 inch Schedule 40 PVC, and it's 65 feet long. Here's our point of connection. And then there are some other pieces of really, really critical information here. So here's our main and our meter. This is indicating that there's a 5-foot elevation difference between the main and the meter. And there's also a 12-foot elevation difference between the meter and the point of connection. And finally, there's a 10-foot elevation difference between the point of connection and the highest head on the system. That's going to be important because, as we discussed in our static pressure lecture, elevation is very critical in terms of how it affects pressure in the system. So that's the basic information we're working with. So we are going to start working now with the Excel worksheet that you see here. So I'm going to be putting numbers into the worksheet here, but I'm also going to show you line by line what each of those is in the presentation, starting with line 1. And the lines that I have listed in the presentation correspond to the lines over here in the worksheet. Okay, so line 1 asks for the static pressure at the source, or the city main, and from our problem we know that that was 80 psi. Now the units are already there, so all you have to do is enter 80, hit enter, and it moves down to line 2. Line 2 asks for the net elevation change from the source to the point of connection. So recall that we had a couple of elevation changes there. We had 5 feet between the source and the meter, and we had an additional 12 feet between the meter and the point of connection. So that means there was a total of 17 feet in elevation change. So I'm going to go back over here to my worksheet. The units are already there, feet, and I'm just going to put in 17 and then enter. And then you will notice, happily I'm sure, that the worksheet has gone ahead and calculated the PSI change due to elevation and given you in lines 3 and 4 that change as well as a static pressure at the point of connection. So that's the beauty of these worksheets. They do those calculations for you. So that's the first part of the worksheet. Now the next part of the worksheet, we're going to be taking into account some of this additional information we had about the pipe that's used in both the service line and the point of connection. So let's consider that. Starting with line 5, the worksheet asks for service line information. Now the first cell asks for the length of the service line. So I'm just going to select that cell, and our service line, we know from our example, is 25 feet long. I don't need to enter units here. I'm just going to say 25, enter. Don't worry about this div over here. It's going to work out as we enter more information. The next cell asks for size, and when you click on that cell, you're going to get a little drop-down menu that comes up, and you're going to be able to select a size. Now ours was 1 inch type K copper, so I'm just going to select the 1 inch. Terrific. I'm going to move on to the next cell. It also gives you another drop-down menu where you can choose the type of pipe, which is K copper. So that's all of our service line information for line 5. Now line 6 asks for the same information for the delivery line. And the delivery line, we know from our example, was 65 feet long, so I just hit 65 and then enter. We also know that it was 1 1/4 inch Schedule 40 PVC, so I'm going to click on this drop down, hit 1 1/4 inch, go to the next cell, and get Schedule 40 PVC. And you'll notice it's already doing a lot of calculations down here that you won't have to. Now the next thing it's asking for is the size of the water meter. That's in line 7. So if you click on that cell in line 7, you can get another drop-down menu, and we know from our example that the water meter is 1 inch, so I enter that. And then line 8 and 9 give you the option of entering additional information. There may be extra valves on the system or some other components, perhaps filters or things like that, that are also going to create some friction losses in pressure. So this it gives you a spot in the spreadsheet to enter those. But in our case, we don't have any of those, so we're going to leave it blank. All right, now moving on to the next lines. Line 10 calculates the pressure loss through the water meter. And I want to go over these, even though they've already been calculated, because they're based on a couple of rules of thumb that you want to keep in mind. So pressure loss through the water meter is calculated, actually, is considered in this way. The allowable loss through that meter cannot exceed 10% of the PSI up here. So it's saying that the allowable loss cannot exceed 10% of 80 PSI, which is 8 PSI. And that seems like a problem here because we've got 36.4 GPM. But let's keep going. So the volume through the water meter, allowable flow of the water meter is considered to be less than or equal to 75% of the maximum meter capacity. And given the fact that we've got a 1-inch meter, the worksheet has gone ahead and calculated that as 37.5 GPM. Okay. Now, another way, or another calculation that's important is the velocity through the service line. And the maximum velocity through the service line cannot be greater than 7.5 feet per second. That has to do with the pipe material and safe operation, as do all of these different determinations of design capacity. So those have all been calculated for you. They range from 36.4 GPM, 37.5 GPM, 18.2 GPM. All three of those are considered, and then what the worksheet does is it takes the lowest one and puts it down here in line number 13 as your design capacity. What it's done is simply choose the lowest one, the most conservative option, because even though the real answer is probably somewhere in between all of these, if you choose the lowest one, you're going to be assured that you have that design capacity. Okay, I'll just also talk quickly about this particular cell right, well, let me select it there. That cell is a design capacity override, and what it does is it allows you to use a number different from what's chosen here in line 12, which is 18.2 GPM, to determine your overall design capacity and available pressure. If you decide that that's too conservative for you, you have the chance there to increase it. But you should certainly have a good reason for doing so if you want to make sure that you've got a good design. Okay, so let's talk about the next section of the worksheet. And in that section, the calculation of dynamic pressure is made at the design capacity that's been determined up here. So our design capacity again was determined to be 18.2 GPM. So I want to put a couple of pieces of information in here. Now, it's already done some of this. So line 14 here, it's actually already put information about the PSI loss per 100 feet based on what we entered up here on line 5. And so it's got a PSI loss per 100 feet for 25 feet of that type K copper, and it's already made the calculations. So these PSI losses per 100 feet are just coming from those same friction loss tables that we used previously. Same thing happened with the delivery line. The appropriate PSI loss per 100 feet was chosen from a friction loss table. The appropriate length, which was 65 feet, was entered, and the PSI loss was determined. So for those two lines, oh, sorry, I missed one here. Let's not forget the water meter. So there's also some pressure loss from the water meter at the given design capacity, and that the worksheet has already entered as 1.84. And that kind of brings me over here to this slide. I wanted to show you just that there is a pressure loss chart for water meters in your textbook, and the basic pressure losses for the water meter were pulled from here for this portion of the worksheet. I've blown up the relevant part of the worksheet here, And basically what we already know that it's a 1-inch meter, and the other piece of information that we also know about it is that the volume through the meter is not to exceed 75% of the maximum meter capacity, which ends up being about 36 GPM, and if we follow that over, we're at about 7.8. So that's where some of that friction loss information is coming from for the meter. But fortunately, the worksheet has already calculated a lot of that information for you. As I mentioned before, we didn't have any isolation valves or other pressure losses. So down here, the total pressure losses from the source to the point of connection are calculated, and it's just added all of these different potential pressure losses together for a total of 5.75 psi. So now let's keep going. Got a little ahead of myself on the worksheet here. Let's keep going. All right. Okay. All right, so we just talked through all of these, and we determined that the friction loss through those components is 5.75 psi. And the next line is pulling line 20. Let me get over to the right spot. The static pressure at the point of connection from up here, it's just pulled that information down here, 72.64 psi. And then line 21 subtracts the pressure loss from the source to the point of connection, which was determined here. So it's the 72.64 psi minus 5.75 psi, leaving an approximate dynamic pressure at the design capacity at the point of connection of 66.89 psi. So that gets us through section C of the worksheet. Now in section D, the available pressure at the highest head is determined. And what has happened is a couple of calculations have already been made here. The first one in line 23, and this is again one of those rules of thumb, it's a 2/3 estimate. And what it does is it assumes a loss of 1/3 of the psi from the point of connection to the worst case head. So it's basically taking this line up here, line 22, the 66.89 psi, and multiplying it by 2/3 so that you end up with 44.82. So that's the first attempt at the estimation of the pressure available at the highest head. However, we have some additional information. If you think back to our example, the difference in elevation from the point of connection to the highest head was 10 feet, and there is a space on the worksheet, if I can select it, to enter that. So we just enter 10, enter, the units are already there, and it goes ahead and calculates a psi change due to elevation, and it further goes ahead and subtracts that from our estimated pressure available, and we wind up with an estimated pressure available at the worst case head of 40.49 psi. And so down here at the very bottom, it's giving you the two pieces of information that were your ultimate goal. It gives you the system design capacity, which is 18.2 GPM, and it gives you the available dynamic pressure at the worst case head. Terrific. It's done all those calculations for us. All right, so there's our example. I've gone through all of that. Our next lecture, we will be going over the situation where you have to calculate an assumed flow.